Many companies use Elastic or OpenSearch, but only use 10% of the capacity. And also they have to build ETL pipelines, get data normalized, worry about race conditions. All in all, at the moment, when you want to do search, but you already have existing data in a data warehouse or in a Postgres instance, you are forced to build a distributed system, but not anymore. ParadeDB is building an open source Postgres extension to enable search within your database. And today I'm talking to Philippe Noël, the founder and CEO of ParadeDB, and we talk about build ParadeDB, how they integrate into the Postgres query engine, and how you can build search on top of Postgres. Let's do it.
That's why we did Rust. And the only two options if you're building Postgres extensions is C or Rust. Although now, since there's another company trying to make it happen in Zig, but at the time that was not possible, and I don't think their project is mature enough to really build like a state-of-the-art product on it yet. Anyway, Zig is just beginning to be possible, and the Zig ecosystem is so small. Most of data infra gets written in Rust nowadays, I would say.
What wouldn't have been possible if you hadn't written it in Rust?
Aside from Tentative,
Yeah.
that's one really big one already. The second one I would say is just the speed at which we can develop. Things would have taken so much longer if we did them in C. So that would have been a big problem. We also built this project called the Analytics, where we bundled in a library called Data Fusion inside of Postgres. That would not have been possible without it. We also played around with DuckDB, that you can do that in C pretty easily. It's probably easier in C actually. So that one is a counter example. We're thinking about new columnar file formats as well for our work to replace Arrow, because Arrow doesn't have good random access memory, random access patterns basically. All of those are written in Rust. The only new file format written in C is Nimble
Yeah.
by Meta. It's not that mature. Yeah.
So you will end up going with Lance?
We
Probably?
will go Lens or Vortex. Yeah.
Yeah.
I don't know if I'm fully happy with what Lens does for us. It's very good, but it's very good for them. I don't know if it makes sense for us. It's possible we use it. And analytics, we are borrowing a lot of the work from Data Fusion. But I agree, it's very exciting what's happening there.
It's like you have the easy entry ones like VV8, Quadra, the newer ones. Then you have Elasticsearch and OpenSearch somewhere in the middle, and then you have the really advanced one, Vespa, basically in like complexity, but also in what you can build. Where would you place ParadeDB in that spectrum? And feel free to add like your own categories, how you differentiate from them as well.
Yeah, I think we're really trying to just be a competitor to Elastic. So I would say feature-wise and complexity-wise, we're trying to be in the same category as Elastic, but we're trying to bring that to the ease of use that maybe the Quadrant and Weaviates are. So for context, or let me put it this way, most people use Elastic. Elastic is the most popular one, right? It's the most popular one for a reason. I have a theory that a lot of new search engines are not very different from Elastic, right? They're also a NoSQL database. They suffer from the same set of trade-offs. Like, sure, it might be rewritten in Rust or a different language, but these are, they're not like orders of magnitude different, right? ParadeDB is trying to be that. We're trying to build it in SQL. We're trying to build it in Postgres, which is the most popular SQL or the fastest growing SQL dialect. I think we can build something that's equally powerful, but solves most of the trade-offs that Elastic has. So that's really where we're trying to place ourselves.
Yeah. And can you maybe, just for anyone who doesn't know it yet, give a quick introduction what ParadeDB is?
Sure. Yeah. So I'm one of the people building a project called ParadeDB. It's an open source project. We're building a competitor to Elasticsearch inside Postgres. So what this means is we're building our full text search and analytics or aggregations inside Postgres. All this is built as an extension. The benefit of it is typically the canonical workload customers have is they use Postgres as their relational database. They're very happy with it. Obviously, Postgres is wonderful at many things, but it's not very good at being an analytical or a search database. But when customers need to do user-facing search, user-facing analytics in their products, they need to bring another search database like Elastic usually and start to move data from Postgres to Elastic. That can cause a lot of issues. You have clusters out of sync, you have data that's not fresh, the cost is much higher, you need to denormalize the data, which means higher data duplication. You don't have transaction safety on your Elasticsearch cluster. ParadeDB solves all of these things by essentially bringing the feature set of Elastic inside Postgres directly. And the
Yeah.
way we do this under the hood is we essentially implement some of the technologies that make Elastic powerful inside Postgres. So we're also building inverted index, columnar storage, complex query builder like you have out of Elasticsearch, where you can string together really complex search query logic and analytics query logic inside Postgres so that we can bring those feature sets.
Yeah, and I think especially in Postgres, part of what makes it so powerful is the query engine that actually optimizes your queries below the hood before it's actually executed. Are you also directly hooking into that component as well for the different search queries you're constructing?
We are. Yeah, we are. We work pretty deep inside Postgres.
Yeah, can you maybe double click on that, how that works and what it actually enables you to do?
Sure, absolutely. Within databases, you have two core pieces. You have the planner. The planner takes your query and essentially plans how the query will be executed. And then the executor will go and execute that query against the storage that you have in the database. Postgres is really extensible and it gives you the ability to hook in at both of these layers. At the executor level, for example, what we do is we intercept queries that have a specific operator that we call the @ operator. For anyone that's familiar writing search queries in Postgres, you know that you can do that with the @ operator. That's the built-in full-text search way to phrase full-text search queries in Postgres. We basically introduce our own that has an extra @. And when you use that, we hook in internally in the Postgres executor to tell it, hey, when you see a query that matches this, we want it to be executed against our columnar storage, our inverted index that has BM25 scoring, for example, which is very important, but it's not existent in Postgres. And then that gets rewired internally to our code paths within Postgres. And that's one of the ways we can do very seamless integration that's significantly more powerful.
Yeah, and maybe on the opposite end is where would you actually see the point where Postgres in itself starts to break as a search database, even with ParadeDB? So at what terms of write, read, load, data size, latency you're trying to reach?
Yeah, good question. So I'm gonna have a slightly different answer. I don't think any load has been a core problem for us now. So there's nothing that Postgres technically can't do at very high scale if you scale it. And our biggest customer is a company called Alibaba Cloud. They're using ParadeDB inside a data warehouse of theirs. The load is truly massive and they haven't seen any problems with it. The area where I would say we're not well suited is when people are working with very large amounts of JSON type documents. So ParadeDB works wonderfully if you have a structured relational format. The bread and butter of the customers we service, they store data in Postgres and they want to keep it there, right? If you're using MongoDB or you're using some sort of NoSQL document database and everything works with JSON, you can do that in ParadeDB as well, and it's going to work well. We have customers that do it, but that's an area where using a NoSQL search engine might make more sense for you.
And so basically it assumes that you put the text field into text fields and not into any more advanced JSON structures.
So we can tokenize any type of column or any data type in Postgres, but it's going to be easier to reason around if your data is structured in tables rather than if your data is structured in JSONs.
Yeah. And what is like the power that actually comes with it when you build on top of Postgres? You mentioned a bunch already, but maybe can you go deeper, especially in the transaction part? Why would I want to have transactions for my search queries as well, or for the queries that are running on my search application?
Yeah, good question. So Elastic, one of its biggest drawbacks is it's known for not being very reliable. Clusters go missing or the data is not fresh because you need to ETL it over and so on. Having transaction just guarantees that your data is consistent, basically, and that's very important. So we work with a lot of companies in the financial sector, fintechs, a lot of them, like financial data, you can't have duplicated data. You can't have missing data. That's just so incredibly important. Imagine you're going to your bank account and you have a missing transaction or you have a duplicated transaction. You're going to be very unhappy. For these folks, it's really important that they have really good data integrity, and ParadeDB makes that possible versus something like Elastic. We have had customers come to us and show us their fintech applications and tell us that the data here is not present in their database anymore. Because let's say you roll back a commit in your Postgres and suddenly that commit didn't get rolled back in your Elasticsearch cluster. That can be a really big pain point. So I would say that's one of the biggest one. That's typically the main reason people come to us. We remove the ETL and we give you transaction safety, which means the data is more fresh and the data has very strong integrity. And then there's other small benefits that ParadeDB has. It's about 5 times faster on a single node compared to Elasticsearch. You don't need to duplicate your data as well, so the cost is much lower. Those things play a nice part of it, but they're typically more like nice to haves rather than the core reason people get excited about what we do.
Yeah. Do you see yourself as part of the larger trend where you combine some new capabilities, like, for example, iceberg tables, also running analytics with DuckDB within Postgres?
We do see ourselves part of a trend of composable data system where people like glue in together more state-of-the-art libraries inside Postgres. We have done some work with DuckDB. I do think one thing that's very important in Postgres is to do the work in the Postgres query engine. So we have tried to cut corner before. We've tried to use DuckDB. We've tried to use Data Fusion to accelerate analytical queries. There's a lot of overhead that comes when you start to jumble in multiple query engines. And we found that to be a big problem. Like it's really hard to give the data integrity that I was mentioning is so important before. So I do think systems will consolidate, but I don't think they'll consolidate and use like all the tools in the exact same way that people think. A lot of the work you just have to build natively in Postgres.
What does this mean exactly for you guys, that you also plan to run the analytical queries, which is like one part of your feature set over time in Postgres, or are you already doing that?
We're already doing that, and we're going to be doing more of it. At first, basically, if you're familiar with Elastic, our core mission is to build an Elasticsearch competitor, right? We started by building the search capabilities, and what we found out is the analytics capabilities are very important. They're a very core part of Elasticsearch as well, and you need both in order to deliver real value. So, if you use like a search engine, oftentimes you'll return results, and you'll see there's 100,000 results that exist on this e-commerce website or something like that, right? That's an example of an analytics query. So we started looking into building analytics. When we did, we first looked at it by using Data Fusion, and then we looked at it by using DuckDB. And each time the performance was really fast. You can get really quick performance really quickly, but it didn't integrate well within Postgres. It was very difficult to get the MVC, right, the transactional guarantees to be really good because analytical engines typically don't really care about transactional safety. That's not a really important part for them, but for Postgres it is. And so what we found out is if we wanted to do that, we need to build it ourselves. So today, in that executor hook workflow that I described, we also store data in columnar format in a fully Postgres transactional way. And then we crunch the aggregate numbers by accelerating the way Postgres operates on that data. And we're not using DuckDB, we're not using Data Fusion. We're building similar designs as what they've done, but we're doing it directly in the Postgres planners.
Does this also mean that the Postgres that runs ParadeDB should be run on particularly hardware to take more advantage of the columnar format your data is in?
Yes, I would say yes and no. We recommend our customers use storage optimized instances. So on Amazon, they're the i4 something series. I don't know what they are on the other cloud providers. Those are quite similar to the instances that are typically recommended for regular Postgres boxes. The reason being, when you're doing database workloads, the biggest time-consuming piece of the hardware is reading the data from the disk, and that's reasonably similar to transactional's workload.
Yeah, and just maybe to catch people up, MVCC basically means that you can have multiple versions of the same row in your
Yeah,
database. So multiple transactions basically can interact with the same pieces of data. And basically each one has a version based on the timestamp when the transaction started.
correct. Yeah, it enables concurrent access, and it's one of the crown jewels in a lot of. There's things wrong with it, but it's one of the things that make Postgres so good. Postgres is known for being really reliable database. Like your data is always there and it's always correct, and MVCC is how that's possible.
Yeah. And especially when I'm looking at Elastic, it's what a lot of people underappreciate is like the analytics that come with
Yeah,
it because it also has a columnar storage format. It doesn't just have the reverse index.
yeah.
What are you planning in there and what are you already offering? Like you usually have click data when we are talking about search, you have personalization vectors, you have re-ranking, all of which is basically more or less linked with the analytics component. How is this working in ParadeDB? And what is the feature set you already have in production right now?
Yeah, so we already have columnar storage in ParadeDB. We already have vectorized processing as well, which is how you can do really fast aggregation over that columnar data. It's not generalized yet. It's not generalized to all click data, for example. It's used specifically in the context of what we call faceted search, which is essentially analytics over full text search results. So that can mean bucketing category results, right? You're a search engine like your Amazon, and you want to bucket results by star ratings, right? 4 star, 3 star, 4.5 stars, things like that. Or you want to count the total number of results that there are, things like that. That's what we do today, specifically in the context of search. As we go, we do plan to generalize it to generalized aggregate operations that you might be able to do on ClickHouse or time series databases or things like that.
Nice. What do you say is at the moment the killer use case for ParadeDB? Because in Elasticsearch, most people don't know, they started out really heavy and still are on log data.
Elastic, when it started, its killer use case was actually user-facing search, and very quickly they moved into observability. Um, what we do today, I would say, is transaction safe, no ETL, user-facing search and analytics. So we power search for financial technology companies, as I mentioned. We power analytics for productivity companies that you probably use. Many of them will be releasing announcements about them in the next few months. Really user-facing search and analytics, dashboarding, tabling, filtering. We're big in sales automation as well. E-commerce is another big one. Those are typically the ones we service. We may go towards the observability world eventually, but first we got to build like a really good foundational database before we start looking at that.
Yeah. And what would you say are the things you want to take with you from the other databases and bring into ParaDB? So, what are the things you actually really like about certain other databases?
For Elastic, for example, I really like it's like the feature richness of the queries, right? You can do so much, and I think it's important to enable users to do that. We had users that requested things like percolation, for example, which is a reverse querying. If you save a search query and you have new data that comes in, it automatically maps the result rather than the standard search, which is store the data but do a search query over it. Um, Something that's a big one. We're borrowing a lot of inspiration from Data Fusion and ClickHouse in terms of how they're processing analytical queries. What they've done is really state of the art, and this is some of the work we want to do on the analytics front inside of Postgres. And then we're also borrowing some inspiration from the folks at DuckDB and other of the data lakes type products. I do believe interoperating with data lakes is going to be important over the next like 5 to 10 years. So we're keeping our eyes peeled for work that we can do there.
Yeah. And what degree of interoperability do you mean by that? Is it actually running search on top of like open table formats as well, or rather offloading work, for example, for the analytics?
For now, we do everything inside Postgres. That's what our customers want. We do have another project that uses DuckDB that can read data from open table formats on S3 or Google Cloud Storage or Hugging Face or things like that. So that makes it really easy to load data into Postgres and then do search and analytics over it. That's one of the ways we interoperate. Eventually, we'll also want to be able to write data to object storage so that you can offload colder data to a cheaper storage mechanism. I do think there will always be a place for hot data that's inside Postgres and then some cold data in object storage. And we just want that transition to be very seamless for people.
What was the thinking behind using DuckDB for reading over foreign data wrappers?
So we do both. We do both.
Yeah.
We have it's built as a foreign data wrapper, which internally uses DuckDB. That makes it just much easier, right? Because DuckDB abstracts away the entire workflow of interoperating multiple file formats, multiple object storage, things like that. But it is a foreign data wrapper using DuckDB inside of it.
Interesting. And also most underappreciated feature of DuckDB, it's like the CSV parser for me.
Yeah, exactly. Yeah. So if you want to do CSVs, you want to do JSONs, things like that, it works quite well.
Yeah, nice. Maybe let's move into the case study you actually posted, the Alibaba Cloud. Can you maybe give a little bit of background what they actually try to build and how they basically ended up using ParadeDB for their specific problem?
Yeah, so Alibaba reached out to us in February of this year, so it's been a while now. They were building a Postgres data warehouse, and one of their customers wanted full text search in that data warehouse. If you want to do full text search in Postgres, there's basically three things you could do. They could use the regular TS vector built inside Postgres. That's very limited, so they didn't want to do that. They could use Elastic, but then they wouldn't really be offering a singular product. They would need to offer two databases glued together, which is not great. Or they could use ParadeDB or try to rebuild it, right? And they reached out to us and decided to work with us and purchase the product rather than rebuild it. And then they integrate it within their data warehouse.
And what is the difference between the data warehouse context and general purpose search?
So that's a good question. I don't think it's that different, to be honest. There's differences in the nuances of how like the data is stored and the type of data and how it gets searched over and things like that. But that's something we've mostly left to Alibaba to figure out themselves. Like they are modifying slightly our work in order to integrate it internally within their product. But from our side, it's just Postgres, right? ParadeDB is building a Postgres compatible product and that data warehouse is Postgres based. So as long as they remain Postgres compatible, a lot of the interoperation of our work with their work is taken care of by the core Postgres query engine.
Yeah, nice. I want to actually double click a little bit more on the complexity behind it. And especially, you already mentioned you have two core different components. On the one, you're hooking into the execution engine, the query formulation, but also the file system, like how the data is stored. Can you maybe take it bottom up? What changes did you actually do to the file system, and how does it actually differ for different types of data? So is for example, text data laid out differently than the data for your analytic queries? So basically the interaction data, for example.
Yeah, good question. So what we do, we create a new custom index in Postgres that we call the BM25 index. For context, for those that are not familiar, BM25 is a ranking algorithm to rank search results. And it's known to be the state of the art. It's what Elasticsearch uses. It's what most powerful search engines use, or all, perhaps even. And Postgres doesn't support it. So we do that. Then within that index, it is an inverted index. So it stores mappings basically between tokens and their location within the tables, in our case, within the documents in the corpus. That data gets stored inside a standard Postgres index, and I'll spare you the complexities behind it. You have a file format that gets stored within the Postgres pages, excuse me. But all this to say, this is how we work at a high level. And then we also have the analytics queries. So we have the ability within our index to specify when you index different types of data or different fields, whether you want them to be indexed as what we call fast fields. Fast fields means they're indexed in columnar format. So if you don't do that, if you use, for example, like a text column, you can store it as a regular inverted index type format. Or if you have a numeric field or an integer field, for example, that you may want to do aggregation over, then we recommend you store it as a fast field. And it's still going to store within the index, but it is going to store as a columnar format.
Yeah. And when I'm looking especially at the comparison of Lucene, you have the segment info, and also you have field data, you have norm data, you have normalization data often, you have the TF-IDF part. What are like the components you actually took with you for the new index you created? What's the additional data you're storing for each?
Yeah, so we do the exact same. In fact, the search engine that we use called Tantivy is very strongly inspired by Lucene. It's not exactly identical, but it's very strongly inspired. So we store the exact same things. All of these components you describe are required to calculate the BM25 score. On top of this, we will store data related to Postgres. So that's one difference compared to Lucene. So as you were mentioning, we will store data to make it compatible with the Postgres index access method, but we have the data stored in the tables. So I don't think we store any extra data. Like the extra data would be like the transaction safety related information, but that's stored within the rows in the tables itself, not in the index.
Yeah. And can you maybe walk us through it? And you setting up a new database, you're inserting all the documents. What's been happening behind the scenes as new documents are hitting the database? What's happening to the documents, how they are pre-processed and inserted?
Yeah, so the Postgres access method, the Postgres has this API called an index access method. That's what developers like us get to define custom indexes in Postgres. When you define your index over a table, it has triggers in place to process new data as it gets modified or inserted. So whenever you have a new row that gets inserted in a table on which you've created an index, a ParadeDB BM25 index, that row would automatically get grabbed by the Postgres index. Is going to be tokenized following the tokenization strategy that you've defined. In our case, all of this is handled by a search engine, Tantivy, that does the tokenization into an inverted index. And all of that is going to be stored on disk. And then when you go and you write a query, that query will be executed against the index, assuming you use the proper syntax. And if you go and modify, you update a row, you delete a row, this sort of same process will happen and will update the index accordingly. What this means is if you make large updates, it might take some amount of time for the indexing to finish. It's quite quick, but it could be half a second, a few seconds, depending on maybe even more. If you're like indexing an entire new table, it can take minutes or hours.
How do you actually allow the user to tailor their search applications for the specific use case by constructing really complex queries, but still maintain like the level of simplicity and deterministic language that in the end SQL brings with it?
Yeah, that's a very good question. That's one of the things that I think we do quite well compared to Elastic. So if you look at our docs, you can see this. We have our general full text search API, where, as I mentioned, we use the @@ operator. So you could define a really simple search query. Look in the search for product catalog where the description mentions blue, right? And you get all the blue items that you might be selling, or keyboard, and you get all the keyboards you're selling, or something like that. So you can write very simple queries with this in almost like in pure PostgreSQL. Now, we also have something that we call the Query Builder API. So our Query Builder API, which is in our documentation as well, is a bit similar to the Elastic DSL. What this means is we expose the entire underlying search engine, exactly like what Elastic does, where you can construct really complex queries. You can do Booleans between results. You can do disjunction max to do type breaking, for example. You have really complex access, and you can do it in SQL, but you can also do it in JSON, similar to how you would with Elastic. That's been pretty important for our customers. Some of them will have the queries be generated programmatically by their application based on what the user will click. It will like programmatically generate the query that they want to run. And that's just easier to do in JSON. So we expose that as well.
Can you give me an example of what query, for example, is constructed as the user clicks through the dashboard?
Sure. So let's say you're a sales automation company, right? You're a product that sends emails on behalf of customers. You might have a table where I'm a user of yours and I can say, okay, I want companies based in Europe that are between 100 and 500 employees that are in the manufacturing space that are less than 5 years old. Let's say that's who I want to email, right? When you go and you click these, behind the scenes is going to be generating a query to say, okay, it needs to take this part of the data set and not this part of the data set, and so on and so forth. So oftentimes those queries get generated programmatically, and it's easier to do that in JSON. So we make that possible with ParadeDB as well.
Yeah. And when you look at the projects and you would see someone setting up ParadeDB for the first time, what would you tell them when they expect they're building a large search applications? How do they future-proof it for like larger scale? What are the settings? What are the setups they should consider from the get-go?
Yeah, good question. The good thing with Postgres is you don't really need to overthink it too much early on because you can always modify these later. Postgres scales vertically very well. So for most people, we ship with a set of defaults that are pretty straightforward, and I don't think you need to modify too much. One thing is we recommend that you set the parallelization parameters of Postgres to match the number of CPUs on your machine. That has a really big impact on performance, specifically for analytics. We have a page on that in our docs. Then, I would say from an infrastructure or an architecture standpoint, we recommend our customers follow the same sharding and partitioning strategy in ParadeDB as they do within their Postgres. It's quite common for companies with larger, basically, when you use Postgres, what a company will do is they'll start with a single Postgres database, right? A monolith that they'll store all of their data in. Eventually, that's going to be too big. They have too much data to do that. So they're going to need to partition the data or shard it across multiple Postgres machines. When you do that, then using something like Elasticsearch can become complicated because you have two different ways to think about how the data is structured. But ParadeDB can do the same partitioning and sharding strategy that your transactional Postgres does. So that's what we recommend customers do. Like any best practices that they're used to doing in Postgres, we recommend they do in ParadeDB as well. And you can define schema migration and database migrations in ParadeDB because it's Postgres. So it's actually quite easy to map that across your entire infra.
What is the difference between searching on a single node versus a sharded database?
So most of the customers that use us in a multiple node today, what they do is they route the queries based on where the data is stored. So let's say they have two nodes, they'll have half of the data on one node, half of the data on the other node. And if you design your partitioning and your sharding properly, you're not going to need to do cross machine queries. So that's going to be pretty simple. Obviously, if you want something like Elastic, where you don't really need to think about it, right? Everything's going to work. ParadeDB does not support distributed search in that fashion today. We have found actually that our big customers don't need it. But when they do need it, then we will probably build it, and then I'll be able to tell you the way we're going about it. We have a few ideas for how we want to do it, but yeah, for now, we haven't dived too deep with it.
Yeah, I would just expect at some point I will hit a query where the sharding strategy was in the end the wrong one.
Usually the companies that shard their Postgres, at least the ones that we work with, they have very smart engineers, and those people have designed it really well. So far, we haven't had that need, but I am certain it will happen for sure. Yeah.
Yeah, once
Yeah.
the less smart engineers are coming in.
It's not that, but you know what I mean. Yeah, eventually it'll happen. Yeah, but for now we haven't needed to. And that's one thing that I do want to talk about. Postgres scales vertically very well. And because ParadeDB works with joins, while Elastic doesn't support joins, you don't need to search over as large a data set. So we have, for example, customers that have 50 terabyte, 100 terabyte Elastic clusters, right? And they come to us and they say, hey, can ParadeDB work over 100 terabytes? Because that's how much data I have in my Elasticsearch. But in reality, the question you should be asking is, can ParadeDB work over my largest table that I put into Elasticsearch? Because if you have 100 tables that are each 1 terabyte, then ParadeDB is going to do very well because it's just 1 terabyte at a time and then you join the result set at the end. In the case of Elastic, they don't support joins. So you have to search over 100 terabyte no matter what, right? We don't have that problem because we have the relational structure. So with even a single node, you can get very far because usually no one has a 100 terabyte table in Postgres. People will have a few terabytes maybe at most.
Yeah, and I think in the end it will come down to the Redshift study that the large majority of data sets isn't even that. And
Yeah.
even if like your queries will only hit a subset. So you
Exactly.
can actually do a lot, especially when joins are possible as well. So you can split up the different text fields, for example, into multiple different tables.
Yeah, exactly. That's one of the really big advantages of ParadeDB. So oftentimes we have customers come and they're like, "Oh, I have this big Elasticsearch cluster," and by the time they use ParadeDB, they're like, "Oh, actually, it works very well. I didn't need to like think about it as such a big volume."
Yeah. How do you actually think about query optimization for ParadeDB? I think everyone knows the explain keyword for Postgres, which is like your best friend if you know it already. How do you think about it in ParadeDB?
It's the same. It's the same. We have made sure that our work, when you run full text search queries, the explain and the explain analyze function also provides you statistics on what happened in the search index and in the analytics side of the search index. This is what our customers use. We try really hard to conform to the way people use Postgres so that they don't need to change their workflow.
Is there any advantage for using Rust for that? Because I think Rust especially is very verbose in any error messages it
Mhm.
throws. Is there any advantage of in the combination of explain and Rust?
That's a good question. I wish I had a better answer for you to that. I would need to ask one of our engineers who's built this. My understanding is the error messages that we return are as much as possible the Postgres error messages that Rust allows us to glue it because again, we're trying to be as Postgres-y as possible. So I don't think we do anything really specific here. But yeah, I'm not sure. I don't think there's anything meaningfully different. But we do have very thorough error messages and they are Rust based. So there's probably some stuff that I'm not thinking of.
Or what would you say are the most common mistakes people do when they start out with ParadeDB and doing search on top of Postgres?
Good question. The most common mistakes, there's a few. People want to do analytics over fields they haven't specified in columnar format. That's a common one. And then they find the performance is not as fast as they expected. We now default your integer for fields to be indexed in columnar format anyways, unless you specify that you don't want that, because most people usually want it. Another one is not configuring Postgres properly. So if you want the maximum performance on analytics, you do need to make sure that Postgres can take advantage of the full hardware. We also have instructions on how to do that. And inside Parade, it comes pre-configured. But sometimes when people are setting up themselves, they make that mistake. And then on the search front, it is not uncommon for people to misunderstand how the tokenization works and be surprised to not find results based on specific tokenizers. We already have some work that we're going to be releasing there to make it much harder for people to make that mistake. But understanding like how n-grams tokenizers work versus like white space tokenizers and things like that. Sometimes people will write a query, it will return no result, and they'll be pretty confused. While in reality, it's not that ParadeDB is misbehaving, but it's just the query isn't quite doing what they thought it would.
Yeah. What would you say? What's on the horizon? What can you already teaser? What's next for you guys? What do you have in the pipeline at the moment?
First, lots of big case studies are going to be coming up. We've been quiet for a few months as we've been making the product even more enterprise ready, but I'm excited to release that. From the product standpoint, we have a lot of exciting works coming around fast analytics. So I'm very excited for that to be released in Postgres. There's a lot of people waiting. Yeah, lots to be announced here over the next few months. And then we have some integrations with some other folks in the Postgres world that will be coming. We've been laying the groundwork to make that possible, but you'll be able to use ParadeDB in more places than you could before. And I'm very excited to announce that in a bit.
Nice. And when you look at the larger landscape, I think there are a lot of people implementing search, implementing RAG right now. What's your dream tech stack on top of ParadeDB for RAG for search? What would you add to your stack when you have to build like a full-fledged search application?
Oh, that's a good question. That's a good question. We work with a lot of customers that don't even use RAG that much. So we ship PG Vector in ParadeDB. It's very common for people to build RAG products using basically ParadeDB with pgvector for the search stack, and then they will use like some re-ranking models on top of it with any of the RAG tooling or RAG pipelines tools that exist. That's typically the very standard one. We don't do a lot of work there. Yeah, I don't know. Whatever floats your boat, honestly. Postgres is integrated everywhere. It varies greatly. Yeah.
Nice. That's usually my place for the hot takes. I often get some people to really get some interesting stuff out there. And what's something that you would actually love to see built in AI, in data, or in search? That's you're not building, by the way.
Yeah, that I'm not building. Sure, of course. In AI, search, or data, let me think. Let me think. For one, I think there's a lot that can be done in Postgres still on the data front around better analytical queries like materialization, like view materialization is a big one that I think can still be improved upon. I wish that would happen. On the search front, I wish, honestly, it was easier to deal with synonyms and with synonyms parsing in a lot of search engines. So now it's being done through vectors in a lot of cases, but we've had a bunch of customers that have wanted things different than that. We may build that eventually, to be honest, but yeah, I wish there were better handling of that. And then lastly, let me see. Another big one that I think will be important is more of the various data tools integrating with object storage. So we've had to do a lot of work on that ourselves. There's tools like DocDB that make this slightly easier to do, but it's still a lot of work. I think the deeper integration between search and analytics engines and object storage would be very valuable for the community. And I know people are working on this for what it's worth, especially in the Rust data ecosystem.
Nice. And if people want to start building the stuff we just talked about, where would you point them?
Docs.paradedb.com. You can see everything there. We have a tutorial and we have everything you need to get started. We have our README, our GitHub README. So we're on paradedb/paradedb on GitHub. And from there, you can also see our Slack community where you can join and ask for help and things like that. It's a pretty vibrant community. Those are the best place to go.
And if people want to follow along with you, where would you point them?
Same thing, give us a star on GitHub. We have a Twitter as well, and we have a Blue Sky now that everyone is moving to Blue Sky nowadays. So you can find us at paradedb/paradedb basically everywhere. GitHub/paradedb, Twitter x.com/paradedb, Blue Sky/paradedb.
So, what can we take away when we are building search applications? I think if you are on Postgres and you want to build search, it's prudent to start with something like ParadeDB, which is an OpenSearch extension just on Postgres, because your data is already there and you can start experimenting without having the additional cost of setting up ETL, setting up an entire new database in Elastic, and also what you have to consider, like hiring engineers that actually know how to work with Elastic. And I think at the moment, it's like database engineers and search engineers, it's two entirely different job types, but also skill sets. One is always hinging on knowing how distributed systems work, and database engineering, especially on Postgres, doesn't. And this also means that it's probably really hard, and thanks to David for that, for pointing that out, it's probably hard to find people on Postgres who know how to do search engineering or relevance engineering, because it will be very different to Elasticsearch, which has the explain, which is an entire skill set you build up over building a bunch of search applications on Elastic. What I think where it's really great, it's like the financial applications. Like you have the transactions, you have the securities, you don't have the race conditions that can happen. When you go distributed or go to Elastic, you don't have to worry about ETL. So it can help in a lot of places. I tried it out. I like the tool. I like the interface, but I also use the Tentify before, so the Rust library, and ran an embedded database, so I was already familiar with it. The explain works. I think it's not as great as in Elastic. In Elastic, it gives you really a lot of information, but it can catch up. Whether we get there, I'm not sure. A massive advantage, in my opinion, is joins, because you can, especially if you have a lot of different searches. For example, like when we talked about BM25, we had GitHub's case, where they have different types of data, like they have code, they have blog posts, they have discussions, they have issues. And each could be its own table, and you can run a search on top of that. And if you want, you can run joins and join it together. Like you can join the repo on the issues and stuff like that. It won't work, like Postgres won't be able to do it on GitHub scale, but if you have a use case which is way smaller, it could be interesting. And what was interesting to me, it's like that JSON documents will give you issues, which I would be interested in actually learning more about why. And what's maybe a good learning for people building, especially like data with query engine, that there comes a cost when you use multiple different query engines, which is a little bit of a trend at the moment, that you mix and match, especially with IBIS, the open source project, that you can actually have one interface into multiple execution engines. So you can use IBIS to call polars, to call Postgres, but it comes with a cost. And one major limitation of it will be like just scale. Postgres hits its limits at a certain point in scale, but it's like when you're running search on Postgres, I don't see any reason to not switch to Parade, because it will be more efficient. And yeah, that's it. I would love to know what you think about this episode. It's very different to what I usually do, like really highlighting a tool and how it works. So I'd love to hear in the comments what you think and whether you want to hear more like that. Otherwise, we will be continuing a series on search next week. So subscribe, and also feel free to comment. It helps me out a lot. I would love to hear critique, feedback, positive or negative. And yeah, see you next week.